All right, everybody. Today we're going to be talking about Chapter 6, which is the three-dimensional structure of proteins. Please note that in Chapter 6, this chapter sort of kind of meanders through a lot of material. So in the efforts to kind of condense this material, I'm only going to ask you to be responsible for these readings. All of Section 1, Section 2, B and C, all of Section 3, and then Section 4A is what we will be covering. All right, again, here are our learning objectives for this chapter. Feel free to pause, print, and make sure that you can do all of these objectives by the time we finish this material. All right, so the 3D structure of proteins, we actually have 4 different levels. We have our primary structure, which is just the sequence of amino acids in the polypeptide chain. Then how these amino acids structure themselves into our secondary structures, such as alpha helices or beta pleated sheets. So a lot of these are derived from the torsion angles around the alpha carbons, as well as hydrogen bonding interactions between the molecules within the polypeptide chain. Then when you get assembly of secondary structures, you have your tertiary structure. So with tertiary structure, you could have 2 helices interacting, or 2 pleated sheets interacting, or more than 2. And then quaternary structure is when you get multiple polypeptide chains or protein subunits to oligomerize in order to form a quaternary structure. So each of these subunits are separate proteins folded into its tertiary structure, coming together at interfaces to form a quaternary or oligomeric structure. Okay, so we've already talked about primary structure when we talked about the different amino acids and how they come together to form a peptide through a condensation reaction. Secondary structure is driven mainly due to torsion angles here and here. Now, in the peptide bond itself, because of the resonance between the carboxylic group and the amine group through the CN bond, we have a planar structure here. Okay, so as we can see in this polypeptide chain, we have a very rigid, fixed, planar structure at the peptide bond, while we're able to have rotation here with our functional groups. Now, these torsion angles about the alpha carbon are called phi and psi. But really what you need to know is that due to R groups and then the carboxylic oxygen and the amino proton, these phi and psi groups are limited with how much they can rotate. And based on the amount of rotation between these phi and psi groups, we get predictable structure. So as you can see here, if you rotate the phi and psi angle too much, you can get steric interferences that limit how far you can rotate these angles. So a Ramachandran diagram, or plot, is a plot that tells you where certain types of structures, based on their phi and psi angles, can occur and which ones cannot occur. So in almost any amino acid, you will not get a phi and psi within these angles here in this quadrant. In this quadrant, phi and psi angle distributions, you get mostly beta sheets, and then some of the collagen triple helix we'll talk about. Left-handed alpha helices occur in this quadrant, and we'll talk about why that is, mostly due to proline. And then you can have right-handed alpha helices or these closed rings in this quadrant. Okay? So based on the types of phi and psi angles that occur in the primary sequence, we can predict basic secondary structure formation. And then we can also tell you what phi and psi angles cannot occur. Now, amino acids such as glycine or proline have a little more flexibility. Glycine, because its R group is just a hydrogen, so there's less steric interference with the different phi and psi angles. And then proline has a fixed, because it has the alpha amine is part of the R group, is bonded, covalently bonded to the R group. So, yeah, the cyclet side chain of proline limits its psi range to angles around -60, making it the most conformationally restricted, which is why it only exists in this quadrant, where glycine, the only residue with a C-beta atom, is much less sterically hindered than other, because, again, that hydrogen is just a proton, so it's not a very big, bulky group, so it can have bigger phi and psi angles. Trying to make sure if I said that right as opposed to proline. Anyway, we'll talk about that more in class on Wednesday if that's not clear. Now, a common secondary structure is the alpha helix. Now, the alpha helix, we see that we get 3.6 residues, or 3.6 amino acids per turn. Okay? We have a pitch of 5.4 angstroms. We see hydrogen bonding occurring between the carbonyl or the carboxyl oxygen of one amino acid and then the amino hydrogen of the amino acid 4 residues away. So if we count, we've got 1, 2, 3, 4. So you see we got 1, 2, 3, 4 residues away, we'll have a hydrogen bond forming. And that greatly stabilizes the helix structure. The side chains, or the R groups on amino acids, are projected downward and outward, as you can see here, from the core of the helix. So these bulky groups are projected out and downward away from the core of the helix. And then atoms in the center of the helix, or in the peptide backbone, are very, very closely compacted and are therefore in some van der Waals contact. So we can talk about dipole moments, stabilizing interactions such as those that occur in the backbone to help stabilize the alpha helix structure. Another common secondary structure is the beta sheet, also sometimes referred to as pleated sheets. These occur when you get hydrogen bonding between neighboring polypeptide chains, and that can occur in either anti-parallel, where you have the N-terminus to C-terminus directionalities are inverted, or in parallel, where the directionality from the N-terminal to the C-terminal is in the same direction. As you can see, hydrogen bonding is different because in the anti-parallel you have direct hydrogen bonding between the two trains. Anti-parallel is usually more stable than the parallel because, as you see here, we actually have an angling of your hydrogen bond, which reduces that hydrogen bond stabilizing effect, so it's not as strong. Now, amino acid side chains are going to be projected either above or below the plane of the beta sheet, and this can increase a lot of interactions between pleated sheets. So a lot of times, residues that are hydrophobic or nonpolar will orient on one side of the sheet, where more hydrophilic residues will orient themselves on the other side of the pleated sheet. So often you'll find amino acid primary sequences that form beta sheets alternate between polar and nonpolar. Let's see. It's not very clear. Okay, come on. Okay, so you can have polar, nonpolar, polar, nonpolar, polar, nonpolar. Okay, and so when that forms the pleated sheet, all of your nonpolar residues are on one face, and all of your polar residues are on the opposite face. So now you can have two pleated sheets, both with hydrophobic faces, forming face to face with each other, and then their hydrophilic faces are on the outside, sort of just like a membrane, right? Like a plasma membrane, where you have your fatty acid tails on the inside facing each other, creating that nice hydrophobic interface, and then your hydrophilic head groups on the outside interacting with water. Another common secondary structure that kind of helps link the alpha helices or the beta sheets, are reverse or beta turns. You have two types that are very common. Type 2. However, in either of these types, residue 2 here is often proline, while residue 3 here is often glycine, and then you get hydrogen bonding between residues 1 and 4 to help stabilize the turn. The reason we use proline at residue 2 is because it already has this nice tight turning capability, with the functional group being covalently bound to the amino group, which just naturally starts to create a turn. And the reason we usually have glycine at residue 3 is because, again, that hydrogen allows the tight turn because it's not a very bulky substituent, so it can allow for this tight turn regardless of where that psi angle, that torsion angle is oriented. So it just gives it a greater degree of flexibility in order to create this 4 amino acid turn. So we often see, the reason they call them beta turns a lot is because this is what will connect a series of pleated sheets to form an overall tertiary structure. So let's talk about fibrous versus globular. So now we're talking more about tertiary structures. So how secondary structures come together in a three-dimensional structure to make tertiary structures. So for a long time, historically, proteins have been categorized as either just fibrous or just globular. However, things we know are always more complicated than that, but it's still a pretty good category. Fibrous proteins are usually more helical in nature, sort of like collagen or alpha keratin. They're usually more structural functions, where globular are more of, variation mixes, as well as coils. So you have coils and mixes of beta and alpha. And a lot of these globular proteins are more maybe your enzymes. So if this is structure, then globular, maybe you can think of it more as enzymatic or other roles of the cell that are not as structural. But again, this isn't just a set definition. This is just sort of a global categorization based on structure composition. Okay? So one of the examples of a fibrous protein is alpha keratin. Now, alpha keratin differentiates itself a little bit from alpha helices because it has a pitch of about 5.1 angstroms instead of 5.4. Now, this is due to the coil-coil structure, where you get two alpha coils coiling together, so two alpha helices coil together. So when that happens, it reduces our pitch. Okay? Now, alpha keratin usually has a 7 residue pseudo-repeat of A, B, C, D, E, F, G with nonpolar residues at A and D. And what that does is as the two alpha helices coil together, they do so at this hydrophobic interface. Coil-coil dimers then will come together. So a pair of coil-coil dimers will form a protofilament. And then protofilaments, four protofilaments come together to form a filament or a microfibril. Okay, so that's the same thing. Now, alpha keratins are also very rich in cysteine. And the interesting thing about the cysteine is, if you remember from chapter 4, we told you how cysteine can form covalent, disulfide bridges. I just erased everything, but that's okay. Let's go to purple, guys. Okay. We're good with purple. All right. So cysteines from neighboring filaments or neighboring peptides, if you want to think about it that way, can form disulfide bridges. If you don't remember this, go back to chapter 4 and read up on that, about how that occurs. So keratin that is very rich in cysteines, and the number of cysteines can vary, are said to be harder. Okay, so if you have more of these disulfide bridges, you make the structure more rigid. Now, if we think about this in humans, people have different variations of cysteines in their hair from person to person. Somebody with straighter hair is going to have less cysteines. Somebody with curly hair is going to have more cysteines. And the more cysteines you have, the more disulfide bridges you have, which is going to create your curl. Now, we can go in and interfere with these disulfide bridges either by heat or chemical treatment, which is then chemically or heatedly straightening your hair. We can also do the reverse by forcing disulfide bridges to occur through a permanent as well. Okay? So just more things to think about in applying biochemistry to real life. So collagen is another example of a helix. This is a triple helix. It's actually a left-handed helix monomers that then come together in a right-handed helix of a triple. So a triple right-handed helix made up of single left-handed helices. The reason we assume the left-handed helix is because there's a lot of proline. So the collagen is made up of triplet repeats of glycine XY, where X is often proline and Y is often a modified proline or lysine. This modification can only occur with the help of vitamin C. So this reaction is dependent on vitamin C. In people who have very low amounts of vitamin C are said to be suffering from scurvy, which we saw a lot on sailors on boats going long distances before. So if they're going a very long distance, we didn't have refrigeration back in exploration days, and these sailors, the fruit would spoil before they set on land, and after a long enough time, their bodies will become depleted of vitamin C. So if you don't have vitamin C, you're not able to form these hydroxylated prolines or lysines, which then cause the collagen to become brittle and weak. And then when that occurred, you would end up with, let's see what it says. You get skin lesions, fragile blood vessels, poor wound healing, and ultimately death. So in order to overcome this, it was started in the British Navy by Captain James Cook, who would provide lots and lots of limes for his sailors, and that's where the term limey came from. So He would issue a sailor 1 lime a day in order to help maintain the vitamin C levels and to ward off scurvy. Now, because of the ring structure, where the peptide backbone of proline is within the ring, is why we get this left-handed helical rotation. Now, every third residue passes through the center of the helix. So of this triple helix, every third residue, as you can see here, will pass through the center of the helix. And because of that, that's why we have to have glycine as our third residue. With glycine being our third residue, the hydrogen is is not a non-bulky constituent, which then allows the crowding to occur. Also, the amino group of every glycine hydrogen bonds to the carboxyl of every proline on a neighboring chain, which further increases the structural stability. I'm going to switch back to red because I think that's a little easier to see. So here we have the carboxylic group of glycine, hydrogen bonding with the proline of a nearby chain in the helix, further structurally stabilizing collagen. Also, the bulky side groups of the hydroxyproline or hydroxylysine and the inflexible proline backbone provides even more rigidity and structural stability. So that's again why if we lack vitamin C, which means we cannot produce hydroxyproline, we then will weaken the structure because we need that bulky side group from the hydroxyproline in order to stabilize the overall structure. So amino acids and globular prolines are usually distributed in a certain way, where non-polar residues are in the interior and charged polar residues are at the surface. Now, the uncharged polar residues will occur at either surface, either in the surface or in the interior, and a lot of times these uncharged polar residues will hydrogen bond with other uncharged polar residues in the interior of the protein, which will then enact further stability and also some catalytic sites as well. As we can see here, there's a number of different intermolecular forces that can occur to stabilize the tertiary structure of a protein, such as hydrophobic interactions in the interior, disulfide bridges between cysteines, hydrogen bonds between amino acid R groups here and here. And then we can even get water bridges between charged amino acid residues or even just polar amino acid residues. And then we can also have salt bridges forming as well. Okay, so think about this when we're thinking about what's holding together tertiary structure, as well as even some of the quaternary structure, are the intermolecular forces holding this global structure together. Now, we can have some common tertiary motifs that occur by assimilating secondary structures. We can get mixtures of beta-alpha-beta. We can have just primarily beta sheet proteins. We can have primarily alpha helical proteins. We can get folds using those beta or reverse turns. And utilizing some of these turns, we can get turns as well as coils. We can get things like a Greek key. We can also have beta barrels. And then just various mixtures of helices coming together with either tight turns or more coil connects. Now, quaternary structure is when you get tertiary folded peptides that are separate peptides. So we have 1, 2, 3, 4, oligomerizing to form one protein, or one overall. So it's 4 proteins, sorry, I don't want to confuse you. So 4 separate proteins or peptides, oligomerizing, to form one active unit. Okay, this occurs in hemoglobin, is one good example. Okay, now often Quaternary structure can be made up of four identical or one or more, quaternary structures can be developed by two or more identical subunits. So it's just the same protein expressed twice or more that come together to form one overall active unit. By doing this, you reduce the risk of mutation or defects by, instead of having one very long protein that folds up into this overall structure, you can have four of the same peptides expressed that then can come together at their interface to interact. This also increases the ability to regulate activity. Say if a co-regulator or hormone or some sort of activator comes in and interacts with this subunit, it may cause some long-distance change in the global structure of Unit 1, which then changes Unit 4, which then will come and change Unit 3, and we can either deactivate the entire protein or activate it for some sort of activity just by interacting with one, or it may require interaction with two subunits or three subunits or four subunits, or interacting with one subunit makes it easier to interact with the second, third, or the fourth, or it may make it harder to interact with the others. And we'll talk about that more when we talk about hemoglobin. It's a really good example of how the interaction of a coactivator with one subunit affects the activity at the second, third, and fourth subunits as well. Now, that's not to say that you can't get quaternary structure from subunits that are not identical. Often you can get maybe two subunits that are identical and then a ligameration of two other subunits that are identical. So you may have these two being the same peptide expressed twice, and then you have these two are the same protein expressed twice, and then until the smaller two units and the larger two units come together, you do not have an active assembly. Alright, so that's basically what we needed to go over for this lecture. It was pretty brief. Basically, again, go over your learning objectives. Make sure that you can answer all of these objectives. And be ready for class Wednesday. We are going to be building a model of an alpha helix three-dimensionally by hand so that you can get a little more idea of how the orientation of the residues can make hydrophobic and hydrophilic surfaces, and then how two of those proteins can dimerize in order to form an oligomer through quaternary or tertiary structure. Okay. If you have any questions, feel free to email me, and I will see you in class on Wednesday.